Well, good afternoon. My name is Dwayne Brown with the Office of Public Affairs, and welcome to NASA headquarters. Well, ladies and gentlemen, we have a 2-for-1 science special for you today. NASA's Mars Reconnaissance Orbiter has made some incredible new findings and eye-watering images of the red planet. And shortly following this briefing, at around noon Pacific, 3 p.m. Eastern, on the West Coast, NASA's Jet Propulsion Laboratory will hold a media teleconference to explain those new findings. For the media joining us via television or on the phone to participate in that media teleconference, call the JPL newsroom at 818-354-5011. That's 818-354-5011. So we have Mars on the West Coast, and we have Moon here on the East Coast. And today, scientists will put in further context and correct any misleading information about the new findings on the Moon that have been reported. We have a lot to cover. I'll introduce our participants. They'll give brief opening remarks, and then we'll open it up for questions. Starting off will be Jim Green, the Director, Planetary Science Division, the Science Mission Directorate at NASA headquarters in Washington. Carly Peters, Principal Investigator for the Moon Mineralogy Mapper, or otherwise known as M-Cube, from Brown University. Rob Green, Project Instrument Scientist for M-Cube at NASA's JPL in Pasadena, California. Roger Clark, Team Member, Cassini Spacecraft Visual and Infrared Mapping Spectrometer and M-Cube Co-Investigator from the U.S. Geological Survey in Denver. And Jessica Sunshine, Deputy Principal Investigator for NASA's Deep Impact Extended Mission and M-Cube Co-Investigator, Department of Astronomy, University of Maryland in College Park. Let's get started. I'll turn it over to Jim.
Thank you very much, Dwayne. We're going to start today by putting the water story in context, a historical perspective, if you will. And to do that, we'll start at the beginning. The generally accepted theory of the origin of the Moon goes like this. About 4.5 billion years ago, an object, perhaps the size of Mars, slammed into the Earth. And as these two objects reformed, and the Moon coalesced from that collision, it lost most of its volatiles, and that includes water. This theory is very consistent with the known observations of the Earth-Moon system that we have today. And in fact, it's quite consistent with the results from the Apollo astronauts that brought back over 840 pounds of rock from the Moon over several missions in the late 60s and 70s. And in fact, we have those rocks, we've made those measurements, and on the average, there's about 50 parts per million of water in the lunar rocks. So what does that mean? If we were to extract all the water in the Apollo rocks, it would fill this tablespoon. In other words, the Moon, as we've known it, based on our theories and based on the observations from Apollo, is a very, very dry object. The next part of our story is Lunar Prospector. Launched in late 90s, Lunar Prospector, with an array of instruments, observed the Moon in its polar orbit and found something startling. And that startling measurement was from the neutron spectrometer. What it was measuring were neutrons that were being emitted by the Moon, caused by cosmic rays that penetrate its surface, generating these neutrons. But over permanently shadowed areas in the northern and southern hemisphere, the neutron flux dropped significantly. Now, one of the absorbers of neutrons has been known for some time, and it's water. So therefore, at the end of the 90s, and as we move into this new era, the generally thinking idea is that the Moon is bone dry, but there may be water at some amount in these permanently shadowed regions in the North and South Pole. Well, what we're going to talk about today is truly a major advancement in our knowledge of the water content on the surface of the Moon. 3 papers will be published in Science today that will illustrate an enhanced knowledge of the percentage of water that exists all over the Moon, and not just in these permanently shadowed craters. In fact, the observations of today we will not be able to comment on how much water is in those craters because we can only measure from these instruments the light that comes back from the moon. These new observations that will be reported here are from 3 major instruments. The instruments are the Moon Mineralogy Mapper, or M-Cubed. This is on Chandrayaan-1. Second instrument is the Visual and Infrared Mapping Spectrometer, or VIMS, on the Cassini mission. The third instrument is the High Resolution Infrared Imaging Spectrometer, or HRIIS, on the Deep Impact, which has gone into an extended mission and is referred to as EPOXI, but it's the same spacecraft. Now, these high-resolution imaging spectrometers make it possible to map the lunar hydrogen content on the surface as never before possible. The measurements from all 3 instruments, I think you'll find by the end of today's conference, as being quite clear, were critical in confirming the findings that we're going to talk about today. Now, before we get started, I want to take this time to especially thank the Indian Space Research Organization, ISRO, that is the Indian Space Agency, for the partnership and collaboration with NASA that has made Chandrayaan and M-Cubed possible. ISRO shares in the credit the observations and findings that we will discuss today. We are delighted that they are here, represented by Mr. Karnik from ISRO. Welcome. And without further ado, I'd like to turn it over now to Dr. Carly Peters, M-Cube Principal Scientist.
Thank you, Jim. Well, the moon continues to surprise us. And that's the message that I hope you will take home with you today. Widespread water has been detected on the surface of the moon. You have to think outside of the box on this. This is not what any of us expected a decade ago, but widespread water has been detected on the surface of the moon. So if we could have my first chart. I'm going to be talking about the M-Cube results and giving you a quick overview of what they are and a few highlights of what we've seen. This particular figure summarizes the observations acquired during what we call the first optical period of the Chandrayaan operation for the near side of the moon, the part of the moon that you're all familiar with when you go outside and look at the moon. It illustrates the distribution of several highly diagnostic spectral properties. The blue tones in this particular image illustrate where we have observed with the M-Cube geometry the distribution of the surface, on the surface of H2O and OH, water and hydroxyl. The green and red tones and the variations amongst them are, in this particular image, are designed to illustrate the location of a variety of mineral species across the surface of the moon, which is what the instrument was specifically designed to detect and map. We will not spend much time on that part. We'll concentrate on the detection of water near the high latitudes in this particular image. Let's go on to my next chart. Because what I need to explain to you right from the beginning is how we detect and why we are so certain that what we're looking at is water and hydroxyl on the moon. We use a variety of spectrometers, the one on M-Cube and the one on the other 2 instruments that you'll be hearing about, to look at radiation that's reflected from the surface and measured with these various detectors. It's measured as a function of brightness, as a function of wavelength or color. In this particular chart over on the left is, you can see right up at the top where the visible part of the spectrum occurs, where your eyes can tell the color of the surface. Moving to longer wavelengths or into the near infrared, you see a variety of highly diagnostic features that are due to the various minerals on the surface. Highlighted over on the left-hand part of this chart is the blow-up of the area that's uniquely diagnostic of OH and water on the surface of the moon. And I've identified in this particular figure where you see the diagnostic absorptions of OH and H2O, as well as the solid form of ice on the surface of the moon. And we'll all be coming back to this fingerprint, this highly diagnostic signature of detecting water on the surface of the moon. Okay, let's move on to my next chart. What's shown here is, again, a summary of the M-cube data. Shown on the left, labeled albedo, is essentially the brightness of the surface of the moon as you would go out and look at it on a lovely moonlit night. That gives you an orientation that you should be quite familiar with. Shown on the right is the distribution of the signature of OH and H2O that M-cube has detected. You can see that in this rendition, our detection is principally at the cooler areas of the moon, namely the higher latitudes. That's because of the geometry of our measurements are typically when the sun is high and the only cool parts of the moon are at high latitudes. You may also be able to see that in the center of the northern area is a relatively bright area. And what that shows you is that there's spatial variability. Some areas have a stronger signature than other areas. And we'll be coming back to that through the discussion. So there's two take-home messages here. One, M-cube detects it at high latitudes. And two, there's spatial variability. And that one area that you see in the northern part is a large crater called Goldschmidt. So we see it at large craters. Let's go to my next chart. In addition to the large chart, now all the previous data I'd shown you we've taken our data and downsampled it 100 times to fit onto one globe. When you look at the individual measurements, you see a lot more detail. And this particular strip is 40 kilometers in diameter. And looking at very, very small, tiny, fresh impact craters, we see this signature shown over on the right, this downturn into the diagnostic properties, absorption properties of water. And what we're showing here is that even at small craters, the size of Meteor Crater, for example, in Arizona, you get this detection of a strong signal. Now, also shown there, perhaps less clear in the back of the room, is the background area seen in this moon, which does not have this signature. So the spatial variability is very important. Okay, let's go on to the next chart. And what this shows is a variety of hypotheses that we and the various team members have been discussing of what physical form this water may occur on the surface. We do not know precisely. We have several hypotheses. We need, of course, more data. But there's a lot of suggestions, in fact, one that we have a firm consensus on, that what we're seeing occurs in the uppermost surface of the moon, of the lunar soil, upper 2 millimeters. And these are a variety of different ways that could occur. It could occur as one monolayer, where these are just a few molecules thick. It could be mixed into the soil. It could be altered minerals on the surface. There could be various gradients within the upper few millimeters. These are areas that we'll be actively pursuing in the years ahead. And with that introduction, let me turn it over to Rob Green.
Thank you, Carly. I'd like to provide at this point a little bit more background on the M-cubed science mission and how we've come here. M-cubed was designed and proposed to measure the composition of the moon. You're seeing that here in this graphic. We know the moon consists of rocks, and rocks contain minerals. On the upper right, I've got a picture of a rock that was returned by the Apollo 15 mission. The minerals in the rocks interact with light differently at different wavelengths. And in the middle, you're seeing spectral signatures. So this is the way those minerals interact with the light through wavelength, and they give us signatures for us to decide what the composition of the surface of the moon is based on these measurements. So we needed an instrument that could measure the surface of the moon, and for every point in the images acquired, we have a spectrum to get the signature to determine the composition. Could I have the next graphic, please? And this is a depiction of the type of instrument we've used with M-cubed to achieve these amazing results. From this graphic, you can see white light is reflected from the moon into a telescope of our instrument. From that telescope, the light is passed into a spectrometer. We break the natural light into the rainbow, into the spectrum, and then record that spectrum for each point in the image, producing an image cube, which contains a spectral signature for each point in the image, from which we can determine the composition of the surface. Next graphic, please. And this is the instrument, a very special instrument, the M-Cubed, developed at the Jet Propulsion Laboratory. Here we are in the clean room during the development process. This gives you an idea of its size. Carly Peters, the principal scientist, is there with her hand out looking at the instrument during the alignment phase. Just to give you a perspective, the instrument weighs about 20 pounds. It runs with the energy of a 20-watt light bulb and is about the size of a desktop laser printer, to give you a feel for what it is. And it's quite a compact little instrument for a very big job, which is to map the composition of the entire surface of Earth's moon. Could I have the next graphic, please? And now I'd like to show you some more of the spectacular results that have been returned by M-Cubed. The image on the left is one of our very favorites. This is one of the first images that came back on the 19th of November, 2008, which showed us on the Chandrayaan-1 mission, we had a working instrument, and we were measuring exactly what we set out to measure, which were spectral image cubes, where we have an image, and then for every point of that image, we have a spectrum underlying it to measure the composition of the surface of the moon. And you're seeing a representation of those spectra on the top and side rainbow panels. So we were very excited to see this result on the 19th of November. I've included another image cube there. This is another spectacular data set collected. This is the Apollo 15 landing site. And you can see the Hadley Rill there, where the Apollo 15 landed decades ago. And I want to summarize that we have, in fact, almost 1,000 gigabytes of data from M-Cubed returned over 10 months, all of this type to allow us to, in fact, cover more than 90% of the moon. And you're just seeing the beginning of the results and some of the highlights from the early analysis of these data. So could I have the next graphic, please? So having shown you some of the data sets, now I'd like to show some of the mineral results from M-Cubed. This is a map of aspects of the mineralogy of Earth's moon. Here you're seeing in greens, purples, and blues iron-bearing minerals that we've been able to map because we have a spectral signature for every point in the image that we've collected. These would be iron minerals that would be similar to the basalt lavas that you might find in the Hawaiian volcanoes, for example. The red areas are areas that contain the mineral plagioclase. Again, plagioclase, we're measuring minerals. And these are, plagioclase is a feldspar mineral, which is also found in earth rocks. It's a common rock-forming mineral. So just to give you an indication that we're also proceeding, in addition to the amazing water discovery, we've also begun our primary mission of mapping the mineralogy of Earth's moon with these data. And now, before I go to the next slide, I'd like to invite you all tonight or over the next week, if it's clear, to go out and look at the moon as you've known it, I've known it, as a white or gray object in the sky, and to realize that with an imaging spectrometer, like M-Cubed, like the other instruments we'll be talking about, really the moon is much more than simply a gray body in orbit around the Earth. It is full of spectacular spectral variation. And this depiction should shift to a movie through the spectrum showing the different colors that we've been able to derive. There you can start to see colors sweep through. This is a tour through the M-Cubed data set collected so far, showing the amazing compositional diversity. For all of those who thought the moon was gray, it isn't. It's full of spectacular spectral content, which we can relate to composition. We've talked a little bit about the water that we've discovered with these measurements and a little bit about the mineralogy. But we're going to know in the next decades much more about the moon thanks to these measurements. And with that, I'd like to pass it to Roger.
Okay, I'm going to talk about the Cassini results and also more M-Cubed results. Cassini flew by the Earth and got a view of the moon on a gravity assist on its way to Saturn back in August of 1999. So it's been a long time. May I have the first slide, please? The basic results of the Cassini flyby of the moon are shown here. In the top are just a normal intensity view from the VIMS instrument and the imaging system, and in the bottom row are the derived results from the VIMS. The temperature in the middle is the map of the water, and on the lower right is the map of the hydroxyl. Now, what's astounding about these results is that the water and hydroxyl exists at all latitudes on the moon in direct sunlight, where it's really quite hot. In fact, hotter at the equator than boiling water. So now the hydroxyl is an OH molecule or bond that creates a chemical reaction with other minerals in the surface, and that will create hydroxyl-bearing minerals. We haven't identified any of the minerals yet, but there's a wide variety of hydroxyl-bearing compounds. Clay minerals are an example of hydroxyl-bearing minerals. Now, the diversity that we see here, there's variations in the intensity of the water signature and the hydroxyl signature. That's telling us that there's some dynamic processes going on. The weathering and reactions going on are different on different places on the moon. Let's go to the next view graph, where I'll show you why this is a pretty difficult detection and why it takes 3 spacecraft to really confirm it and make it a solid detection so that many scientists will believe the result. First, the amount of water is small, so our best estimate right now for the amount of water is about a ton or liter of water about a quart or liter of water per ton of lunar material, and that's lunar material in the top part of the surface, the top couple of millimeters. The detection results in a very small absorption band that is shown here in gray on this graph, and you see results from 2 instruments, the M-Cube and VIMS, give very close to the same answer, which is what we were looking for to verify that the calibration is accurate between the instruments. Further, the M-Cube doesn't go as far out in wavelength as the VIMS or the Deep Impact spacecraft does. So the VIMS and Deep Impact can see water in hotter places than is easy for the M-Cube instrument to see it. We will continue to work with the M-Cube data to try and work on detecting water at lower latitudes, but the VIMS and the Deep Impact have an advantage here. And you can see that we see more of the water band, so we can better define it where the heat is coming out. The moon is quite hot, so these red dashed lines on there are the thermal emission from the moon before we removed it from the spectra. So we have to remove the heat before we can see the water well, especially at the lower latitudes. Now, M-Cube, however, has an advantage in that it's orbiting the moon. So if we can go to the next slide, we'll look at some of the high-resolution data or the we've covered most of the moon at this kind of resolution, 140 meters per pixel. And this is a small crater on the far side. That's on the right or left-hand side of the image here. And on the left is shown just the infrared intensity, but on the right is shown our derived water abundance. So we see this meteor has come in probably within the last 100 million years and exploded the surface and spewed that material out onto the surface, and we see that with M-Cube as a water-rich ejecta blanket. Now that's only part of the story. The ejecta blanket and water-rich nature of it goes in all directions, but in a moment we're going to put on the hydroxyl, and you'll see the hydroxyl doesn't go in all directions. Here, well, it just came up. The hydroxyl comes out mainly at the 1 o'clock and 7 o'clock position. This is typical when a meteor comes in and ejects material from the surface that is buried in the surface. So if this interpretation is correct, and we'll be studying this further, this implies that these recently fresh or young craters have excavated water and hydroxyl-rich material in the surface, and that implies that there is areas around the moon where there's more water than just on the surface. We see a lot of these craters. Carly showed some other indications of some even smaller ones. There are also craters that don't show this effect, so there's a lot of different interpretations to do, and we have a lot of work to do to go through the M-Cube data and perhaps future missions. And with that, I'll turn it over to Jessica.
Thanks, Roger. I'm going to share with you the results from observations from the Deep Impact spacecraft. Since July 4th of 2005 and our successful impact experiment with the comet Tempel-1, the Deep Impact team has been on an extended mission, which will be culminating in just over a year from now in a flyby of the comet Hartley-2. Along the way, we've made several observations of the moon for calibration purposes. And while our spectrometer was obviously designed for cometary observations, it is ideally suited for measuring the OH and H2O absorption features that you've heard described at 3 microns. So if I could have my first graph, please. In purple on the left, you see the location of data that we collected in 2007 over the equator. And then in blue, the northern polar regions that were collected this past June. On the right, you see the corresponding spectra. And with the Deep Impact spectrometer, we now unequivocally see the entire water and OH absorption feature. And that's the areas that are shaded. The feature is relatively strong in the blue polar regions, whereas at the equator, which is the data in purple, which of course is much warmer, there is still a distinct feature, but it's much weaker. Now, we can explore this variability in more detail looking at the full range of the data that was collected in June of this year. And if I could have the next chart, please. On the left is a location image with Clementine data showing our vantage point looking at the northern polar regions. Right next to it is the black and white brightness image, which is constructed from the Deep Impact spectra. It shows you the two basic lunar materials, the bright highlands and the dark volcanic maria. I should point out that we took this data from a vantage point of 8 million kilometers away, which is a little bit different than M-cubed, which had an advantage of spatial resolution because Chandrayaan-1 was in a 100-kilometer orbit above the moon, which makes a great comparative data set. In orange, you see the temperature map that we derive from our data. Not surprisingly, you can see that it's warmest on the right because that's where the sun is. Once we remove these thermal effects, as Roger explained, we can then measure the overall strength of the absorption features. And you can see there's significant variability in this water signature. We have the strongest amounts of water on the left in red and the weakest on the right in blue. And if you look at all three of these images together, you can see that the water signature is not correlated to brightness. It's not correlated to the terrain types, but it is very correlated to temperature. So if I could have the next graphic, please. It turns out that we were very lucky in June because we happened to take observations twice, on the 2nd and the 9th. And in that 1 week of terrestrial time, which is a quarter of a day on the moon rotated 90 degrees. And this allows us to look at the strength of the absorption features as a function of time of day. So for example, in the upper left, you'll see a dark Mare region labeled M, which is in the morning on June 2nd. It has just rotated into sunlight. But on June 9th, on the lower left, you can see that it is near local noon. Similarly, we can look at one of the Highland units, which are labeled in H, in black and H. They started on June 2nd at noon, but by the 9th have now almost rotated out of sunlight and are in the evening. And if we look at the spectral properties, for example, of this Highlands unit, we find some interesting results. At noon, shown in red on the right plot, the absorption is relatively weak. But in the evening, we have a much stronger 3-micron absorption, and there's also actually a difference in the change in shape. And what we found when we looked at all of our data was a very systematic pattern where we had strong absorptions in the morning, they weakened as we approached noon, and then increased again in the afternoon, and finally by evening had returned to the same steady state that they started with in the morning. And so the important point here is that we're seeing an entire cycle of loss and recovery of water features that's occurring during the daytime. And in the next slide, I'll try to give at least one explanation for what might be going on. This is a schematic illustrating just one possible explanation of our observations. During the daytime, the moon is exposed to the solar wind, which includes hydrogen ions. So if you look on the lower left in the morning, which is relatively cold, the blue and the green areas, the hydrogen ions are able to interact with the oxygen in the lunar soil to form and accumulate OH and H2O molecules. By noon, in the center, where the moon is its warmest, the red areas, there's significant water loss. Then, as the moon cools down towards evening, it's able to once again interact with the solar wind and accumulate water and H2O molecules, and we end up at the same place that we started in the morning. This cycle means a number of things, one of which is that regardless of the location or the terrain type, the entire surface of the moon will be hydrated during at least part of the lunar day. I'd also like to note that if this is actually the explanation for the water signature that we've all been talking about, and it may not be, but if it is, this same process would cause similar hydration effects throughout the inner solar system on any oxygen-rich body that doesn't have an atmosphere. And that would include, for example, Mercury and many asteroids. And with that, I'll pass it back to Jim.
Thank you very much, Jessica. So as you can see, there's a new dimension in the water story about the moon. We've discussed things that aren't in permanently shadowed craters. However, we find that there are a number of important scientific results that we need to make sure get stated appropriately. So the takeaway message is this. The observations presented here show a combination of hydroxyl, OH, and H2O that resides in the upper millimeter or few millimeters of the lunar surface. The average amount of water reported, if we were to extract it, is about, as Roger mentioned, a quart of water per ton. So, as another analogy, for 1,000 pounds, that would be 16 ounces of water. Also, as I mentioned, for 1,000 pounds at the equator, that would be 2 tablespoons of water as observed from the Apollo perspective. From a scientific perspective, the difference between the northern regions with this amount of water and the equatorial regions are truly astounding and are generating much scientific excitement. However, please keep this in mind that even the driest deserts in the earth have more water than are at the poles and the surfaces as we've presented here of the moon. Currently, there are no complete explanations for this phenomena, and I'm sure the observations from M-Cubed and other spacecraft in the next several years will continue to bring out more questions that need to be answered about this phenomena. And this will be studied for many years to come. And with that, Dwayne.
Thank you all. Okay, what we're going to do, we're going to open up for questions, and we have a number of media on the phone line. So we'll go to the Ames Research Center, and then we'll take calls on the phone line. So we will go out to Ames.
Hi, this is Mike Swift, reporter with the San Jose Mercury News. The L-Cross spacecraft is scheduled to impact the moon on October 9th, I believe. What more do you expect to learn from that mission in terms of either the quantity or the state of water in the polar regions of the moon?
Let me jump in here.
Given these findings?
This is Dwayne. We have with us our exploration officials, so we're going to give them the mic and identify yourself and can respond to that, please.
Yeah. I'm Michael Wargo. I'm the Chief Lunar Scientist for Exploration Systems, and we're really excited about the results that we're hearing today. And as the question indicated, we're conducting an experiment on October 9th that will look at the potential for water in one of the permanently shadowed craters on the moon's south pole. One of the differences, though, is that the way in which we're going to be conducting that experiment is it's going to excavate the lunar surface, go through that upper surface and down on the order of a meter or so to look at the potential distribution of water ice and other volatiles in the upper meter or two of the lunar surface. So different kind of question that we're answering, and the water question for the moon is a complex one. I think we're hearing that today. And just because there is water at the surface at the mid and high latitudes doesn't mean that it can't exist as water ice in the permanently shadowed regions. In fact, what we heard today was a potential explanation for how the water gets into those permanently shadowed regions. So these are really complementary experiments that are being done, and it shows how exploration enables science and science enables exploration here. So NASA together is moving forward on the on helping to answer the water question for the moon.
Thank you, Mike. We're going to go to the phone lines now, and we have Clara from space.com. Clara?
Yes, hi. I was hoping you could talk a little bit more about theories for the origin of this water. Does the recent findings indicate more that the solar wind origin might be a better idea than cometary impacts?
I can address this. This is Roger Clark. I don't think so at this point. I mean, there's many models out there, and probably to some degree they all are in play, and it's more a matter of working out what the proportions are. So, yeah, it's too early to tell.
I think it's likely there won't, this is Robert Green, it's likely there will not just be a single mechanism, and that, just to echo what Roger is saying.
Okay, we'll now go to Keith Cowan on the phone.
Keith Cowan from NASAWatch.com. Can you hear me?
Yes.
Question. You have had two other space went by the moon making observations, one in November of 2008 and another way back in 1999. Given that you're putting both of these as being corroborative to the more recent data, why wasn't at least the information from Deep Impact published or released to the public? Why did you sit on this or
This is
not
just
analyzed? And most certainly, why any information here not released back in 1999 or 2000?
Well, let me start with Deep Impact, and I'll have Roger talk about the VIMS data.
He broke up so much. Please restate a question that you will answer.
I think he was asking that why, given that some of the Deep Impact data dates back to 2007 and the Cassini data dates back to 1999, haven't we been talking about it before? The answer for Deep Impact is that the data we collected in 2007 was over the equator, and as you saw, it's an extremely weak feature. We weren't looking at it for anything but calibration purposes, and it wasn't until after we actually recalibrated the instrument with the new 2009 data, which remember we took for calibration purposes, that we were able to go back and see that very weak feature in 2007, which is a long way of saying is we didn't know it until very recently. In fact, it was the last thing that was added to the paper. Now I'll let Roger answer Cassini.
Okay, Cassini flew by the Earth in August '99 to do a gravity assist. We were able to turn on the spacecraft for a brief time to acquire data as we went by the moon, and in fact, we also intended it for calibration purposes. But we had no other calibration data until we were approaching Saturn in 2004, when we started our looks at stars, and we also have a solar port, so we're looking at the sun. Every spacecraft that is launched from the Earth, when it's made in the lab, there's so much water around the Earth, and water is such a sticky molecule that it sticks to all the surfaces. So every spacecraft that's out there right now at the moment has water all over the spacecraft sticking to it. And spectrometers can see that, and it's quite a challenge to calibrate the spectrometers so we're not seeing water everywhere. So it took from 2004 through 2008 to acquire the data on Cassini to calibrate out the signatures of water. We were actually seeing stars with water in them, which we knew was not correct, and we traced it down to the calibration of the instrument. And so it wasn't until last summer that the calibration was good enough, and the first papers with this new calibration have been submitted only starting in January. So it's really been a calibration issue.
Okay, our next question is from Andrea Thompson from space.com.
how it's thought that this water might sort of be mobile and move to the poles. I'm not sure I quite understand how that might work.
Could you repeat the first part of your question again, please?
Oh, yeah, sorry. I was wondering if you could explain how you think that the water molecules are mobile and how they might be moving to the poles. I don't quite get how that would work.
Sure, I'll take a stab at this. This is one of the questions that we would like to have addressed as well. As you've seen, this is an entirely new phenomena that has not been studied in great detail until we had conclusive evidence that it even existed. Some of the things we do not know is what is the relative proportion of water and hydroxyl. We have very strong indications that some of this is time varying, both in the M-cube data and the deep impact data, but we don't know in what way it's varying. Is it mobile, or is it being created and destroyed on a rapid manner? We simply do not know these issues. It's intriguing, and we certainly want to go back and try to identify what is needed to address those very questions. We have to understand the physics of this silicate surface and the vacuum around it, which is awash with solar wind particles, micrometeorites. This is an environment and interface that we know very little about, and the physics is just in its infancy.
Well, I can address a little more on that. This phenomenon is actually observed a couple of places in the solar system. Basically, the idea is that where it's hot, water molecules will tend to evaporate, and they'll fly off the surface, and gravity will pull them back down. So the molecules are hopping around if they're not swept away by a magnetic field or solar wind or something. So where it's colder, the molecules will stick longer. So as the molecules bounce around, when it gets to the cold polar regions, they'll stay there. We observe a frost buildup on satellite of Jupiter, Ganymede. Voyager got some very nice pictures of those. The Saturn moon, Iapetus, has a very dark hemisphere, and it looks like water has migrated to the poles. So we see this kind of migration on other bodies. So it's just a surprise to see it working at the moon.
Okay, and I would like to add, this is Jessica Sunshine, that it's just a hypothesis that it's migrating. We have no evidence of that. It's very unknown. One of the variables we didn't talk about is that water photodissociates very quickly, certainly within a terrestrial day on the moon. And so there's a lot of what you're hearing here is basically there's a lot of unknowns that we need to work out to try to explain what I think is a tremendous set of observations.
Yeah, there are many more, Rob Green, there are many more questions today than we had 6 months ago. And there's going to be a lot of work, as Jim has said, over years and probably decades, understanding this phenomena and following up on it.
Our next call is from Ken Kramer from Spaceflight Magazine. Ken?
Hi, thank you very much for taking my call. Yes, I wonder if you could describe a little bit more the mechanism of this water formation via the solar wind. Are you conducting any lab experiments? And was this hypothesized before you got this data at all? And a second question, is there any, what is the follow-up with LRO and Deep Impact? Thank you.
You want to take
I'm certainly not doing any lab work yet. We haven't had time. I don't know about you, the rest of you guys. We just said, I think, most of the first question, which is we don't really know what's going on yet. And by we mean the broad community, and we certainly need more expertise than is sitting in front of you to answer these questions. To answer your deep impact question, we have sadly made our last observation of the moon after we've done our last gravity assist. Happily, that's put us towards our primary target, Hartley 2, but we won't be able to do any more observations here.
But hydrogen has been found to come off the Apollo samples, and solar wind has been hypothesized to be trapped in the lunar regolith, so in the soil. So, we expect at least some of the signal to be due to that effect.
Okay, next question is from Charles Rotley at Examiner.com. Charles?
Hello, Charles Radley. I'm interested in the diurnal variation that was observed by Deep Impact. the lower absorption during the day and the higher absorption at the dawn and dusk. Have you noticed any difference between the dawn and dusk side that might indicate if the accumulation is continuous during the 14-day lunar night, you might expect to see more on the dawn side?
Right. That's a very good question. The answer is within our detectability, we don't see a difference between morning and evening. We don't see an accumulation at night, which you might expect if condensation was going on, for example. And that is what drove us to this concept that we had a cycle that was going on during the day.
Okay, we're going to come back to NASA headquarters with a question. Sir, can you give your name and affiliation?
I'm John Mulligan from the Providence Journal for Dr. Peters. I wonder if you could take us back to November and relive for us the moment when this information began to arrive. Where were you and what were you doing? How long did it take to apprehend what was happening? What did you feel?
There's a lot in that question. Actually, both Rob and I were in Bangalore when the data first started arriving, and when we saw the first image, we were elated.
There were tears in our eyes when we saw that first image come back. It's been a long ride.
And then through the 10 months, the data have been acquired. Obviously, the ISRO operations played an incredibly crucial role in carrying out this successfully. But we do, as Rob had mentioned, have 90% of the surface of the moon covered at the kind of resolutions that you were looking at today. Getting back to the water itself, when the M-Cube team first saw this signal in our data, we, like most other teams before us, had immediately assumed, oh, this is calibration. It's not possible. The moon doesn't do this. But as we discussed further, and when Roger brought in the VIMS data to show us, it became clear as the M-Cube data accumulated, the VIM data became stronger. This was something we could not ignore. And within our team, we spent months trying to find what was wrong.
Trying to disprove this.
Trying to disprove it. Clearly, there must be something we've overlooked. We tried everything, and we could not find anything wrong with either our data or the VIMS data. And by that time, we about decided, okay, we should start writing and prepare for publication. We'll still put a caveat in there because maybe there's something that we just haven't thought about. But then Jessica reminded us, well, Deep Impact is having this calibration flyby, and we'll be able to look at the moon. And we said, okay, so they did, and Jessica got the Deep Impact team to process that data real fast for this problem. And the rest is history now. It is completely conclusive. There is no question whatsoever. And here we are.
Okay, we have time for maybe a question or two. We've got to reconfigure for another event here. So we're going to go back to the phone line. James Dean from Florida Today.
Hi, thanks. Other than as a resource that astronauts might be able to use, I was just wondering if you could speak a little bit to what the key implication of this finding of more widespread water is. Does it say something about, is it more about the understanding the formation of the moon, or does it suggest new possibilities for life in other places?
We probably will have 4 different answers to that. Let me start out. This is Carly. First thing we need to know is what the source of this water in H2O is. Is it solar wind? Is it a comet? Is it meteorites that have accumulated on the moon? Is it from the interior? There is a possibility that degassing from the interior from time to time. We simply don't know. And those are fundamental science questions that we need to understand about this silicate body.
Yeah, I think I'll let Jessica pick up the next.
I think you did a good job, Carly.
But it does have implications. This is Jim Green. As Jessica mentioned, in other
Thank you.
nearly airless bodies in our solar system. That's also quite exciting.
Thank you, Jim. Yes.
But it's also important because here's a discovery of a couple of ways. One, it's a method that we can use to find water from orbit or on the ground with landers. I mean, astronauts could use instruments like these, rovers, all kinds of instruments could be used to search for water in these hot environments, do probing of all kinds of things, not just the moon, all instruments. We do have imaging spectrometers around a lot of objects now. But for the moon, it's important because before this press conference and before our colleagues have learned about our papers, this was thought to be impossible, to have water on the surface of the moon in hot sunlight, especially at the equator, let alone the higher latitudes. So it's a really profound discovery.
Could I have a small addendum, because I just thought of another one. And that is that most of us are geologists, and we get very excited about how planets form and evolve. But this phenomenon clearly has to be a marriage between geology and space physics. And this is going to be a really productive interaction over the next few years.
Okay, time for one more question on the phone line. Raphael Jaffe from Aerotech News.
Yes, question I guess for Jim Green. Do I understand correctly that M-Cube is like a passenger on an Indian satellite that is surveying the moon, and the associated one is there a similar instrument on NASA's current Lunar Reconnaissance Orbiter, which I believe is even now mapping the moon in more detail?
Yes, I'll take part of that question. This is Jim Green. Indeed, NASA has opportunities that we call missions of opportunity, for which individual investigators may propose, and if their proposal is scientifically the best, can be selected, build those instruments to fly on other agency spacecraft. And indeed, M-Cubed is a guest instrument on the Chandrayaan-1 spacecraft built by ISRO. In terms of LRO, that is an Exploration Systems Mission Directorate mission. And Mike, does LRO have an M-Cubed?
Well, NASA has an M-Cubed, and of course, we're going to be taking advantage of all of the data that's coming back. The Science Mission Directorate invited me during the review process to be looking at M-Cubed for its value to exploration, and that's just perfectly clear. On LRO, we have complementary instruments that are also addressing the is there water on the moon question, looking in different wavelengths than the infrared and far infrared. We have a Lyman Alpha mapper that looks at the complete other end, at the very short wavelengths, looking for a signature of a similar type of absorption, but for the lower wavelengths. Additionally, we have a lunar exploration neutron detector that takes another step toward looking at those low energy neutrons that's a signature for hydrogen on the moon. So LRO is also going to be adding to the wealth of information about the moon, providing the best maps available, and also contributing to answering the question and the ongoing story of water on the moon.
Okay. Thank you, Mike, and thank you, panelists. We're going to wrap it up. You can, of course, go to www.nasa.gov for all the exciting new findings, not just here for the moon, but on an upcoming Mars briefing. That briefing teleconference will also be streamed on the news audio. My congratulations to the folks here on the West Coast. Clearly, NASA is an agency for the people, by the people, and it's where science never sleeps. Thanks for joining us.